All right, so absolute risk aversion. Okay, absolute risk aversion is defined as, let's just call it A equals to negative second derivative of utility function divided by first derivative. And as we already mentioned, this is usually negative, this is usually positive, as long as the investor likes money, likes X, and risk averse. Okay, so that's what you would expect. Now, if you think about a diagram like this, right? This is risk neutral. And this is risk averse. It's quite clear that what happens is the slope is decreasing, which means the second derivative has become more negative, right? This become more negative, sorry. So it's decreasing. The second derivative is decreasing because that's why it's becoming like shallower and shallower towards the end, because the second derivative is becoming more negative, making the first derivative smaller and smaller as you go. So because the second derivative becomes more and more negative as the individual becomes more risk averse, once you take the negative sign, A would become bigger and bigger as the individual becomes more risk averse. Right? So A goes up with risk aversion. And why don't we just use the second derivative? After all, the risk aversion really comes from the second derivative, not the first. Now, the reason is this is for normalization. Utility, remember, utility is a rank. You know, this is something you should learn in basic microeconomics. Utility supposedly is a rank, right? So, and in particular, utility is preserved under monotonic function, right? A strictly monotonic function. You should have learned that. Utility is preserved under strictly monotonic function. If you do not have the first derivative in the denominator, then you would have gotten much bigger A for utility functions that really represent the same preference. So basically the first derivative is there to normalize the number. Okay. So that's one measure, and the second measure, the relative rate of risk aversion, so this usually called R, is the negative second derivative multiplied by X divided by the first derivative, and you can see that it really just is the absolute rate of risk aversion multiplied by X. By and large, it does exactly the same thing, because X is just going to be increasing with more X. So why is it here? Or why is it called relative risk aversion? If you take X as money, what it says is your risk preference depends on how much money you have right now. Okay, that's why it's called relative risk aversion. Your risk preference is relative to what you have right now. The absolute risk aversion does not depend on your current situation. It's just say this is your risk preference, no matter whether you are a student or Bill Gates, which doesn't make too much sense, right? You would expect someone with more money like Bill Gates or Warren Buffett would have a lot more appetite for risk than a student. So that's the reason why there's relative risk aversion. This is to make sure that well, your people's risk preference scale up with their wealth. And by and large, this would make a lot more sense than this measure will not make a lot more sense than the absolute risk aversion, because as you will see next, if you assume people have absolute risk aversion, it literally means that they will always invest in the same amount of risky asset, no matter how wealthy they are, which doesn't make too much sense. But the downside is the math involving utility functions that concerns relative risk aversion in a particular way might be harder to solve. So you will see that in a lot of examples, we will use a particular utility function that has constant absolute risk aversion. So that's the next part. So I'm going to. Okay, so utility functions. So you have the CA constant absolute rate of risk aversion, CARA utility, which is UX equals to negative E to negative A times X over A. And it means always invest the same dollar amount in risky asset regardless of wealth. Okay, and then you have the CRRA, constant relative rate of risk aversion, and that one is the UX equals to, okay, it equals to X to 1 minus R over 1 minus R if R is not 1, but it's just log X if R equals to 1. And why is that the case? Basically, you can derive that from integrating the first derivative. The first derivative and the second derivative is what we really want. So by integrating the first derivative, that's what you're going to get. Okay, so this means always invest the same proportion of wealth in risky asset. Right? So these are the two utility functions you're going to see. Okay. So CRR is actually easy. As you can expect, it's just log R, right? So this is what you expect. What about the CARA utility? The CARA utility has to have the same shape because concave function is what defines risk aversion. So but this number, okay, this is not a very good drawing. So this is how it looks like. If you try to figure it out, this is how it looks like. It's actually always negative, right? The actual value of the utility function is not as important as the difference between different choices. So even though utility is always negative, doesn't mean that the investor is not happy. It's just we're talking about which one is higher or not, right? So, all right. So we're going to talk about the simplest possible investment opportunity. So this is the single asset optimization. And so risk-free return, our risky return, R plus S, and the question facing us is, given a wealth of a certain amount, W, and that's in dollar amount, how much should the investor invest into the risky asset? Okay. So theta is what we need to figure out. This is what we want. And so what you do is, well, you first write down the expected wealth, right? The expected final wealth. What do you expect to get on average? Expected final wealth is, well, we're going to put theta dollars out of W dollars into the risky asset, and then the rest we're going to put in the risk-free asset, right? So we're going to have W. We're going to put theta. This is dollar amount. Remember, this is dollar amount into the risky asset. This gives us R plus S return, right? This is R plus S return. And then the remaining, so that would be W minus theta, would give us a return of R, right? Then this is our final wealth. You can simplify that. That would be, I think, WR plus theta S, right? And basically what you need to do is to find optimal theta, you would need to take the derivative with respect to theta of the utility of the expected final wealth. That's kind of what you need to do, right? Regardless of whether there's risk or not, this is what you do. Without risk, this is actually very easy. With risk, it's more complicated. And in particular, with risk, you might not have a closed form solution. That's why it would need specific assumptions. So without risk, easy. With risk, may not have closed form solution. Which is where the utilities that we mentioned just now comes in. When you have quadratic utility, it's almost always, you always have solutions. That's easy. With CARA utility, you will, and CRRA utility, you would be able to have solution if the stock is normally distributed. In some sense, these are the reason why we use these utility functions. We want to say stocks have normal distribution, like stock price moves around with normal distribution. What utility function would give us a closed form solution? Well, those are the ones that you can consider. Okay, so to get solution, you need specific stock return distribution and utility function. Ooh, wow, how long did I talk for? Okay,
an hour and 15 minutes. How long is our class? Till 1:15. So, okay. How does that work? Wait, how does that work? When should I have a break? See, so if I break now, then I have another 1 hour and 15 minutes. Is that the case? Yeah? Okay, so let's take the break now. Right, so as I said, with RISC, you would need to specify a particular return distribution and utility function, and that's what we're going to do next. One of you raised a very good question just now. Right now, I assumed R is like a gross return with the principal, right? I assume R is something like 1.05 or something, okay? And S is not. S is just the addition above that. It might be more natural to express R also as just the net return, and then you have 1 plus R instead. It doesn't actually affect the math in this case, as you'll see in a moment. It doesn't actually affect the math because the 1 plus R, the 1 part, which just goes away, but it would be it might be more clear if I maybe next year. Maybe I'll change that too. But right now, R is gross and gross return. R is gross return, and S is just the addition above that. Okay. And the example we're going to use is CARA. The math is simple enough that we can handle that. And for CARA, constant absolute risk aversion, the assumption is you will need the return. You will need the risky return to be normally distributed. Okay. So with mean, mu, and standard deviation, sigma. That's a very standard assumption. It's important to note that, well, this would be an acceptable assumption in the short run. In the long run, it's not a very good idea to say stock movement is normally distributed. But for short run, it's good enough. So normal distribution, how does it look like? I think all of you should know how it looks like. Normal distribution looks like this, right? Maybe I should, okay. So the bell shape, right? Bell shape, and this would be the mean return, okay? Okay. So this is a distribution of stock return. It's a symmetric bell shape. And I think you should know the properties of normal, right? The properties of normal distribution is if A is a constant, S plus A is also normally distributed. Right? And furthermore, S times A times S. So to make it more clear, maybe I should just, so A dot S is also normally distributed. Right. So normality is preserved under addition and multiplication of constant terms. Now we're going to introduce something called log normal. If S is normally distributed, then E to the power S, so the exponent of it, S, is log normally distributed. All right. So log normal distribution, how does it look like? The log normal distribution looks like a skewed normal distribution because you are multiple. So you can imagine that you are so the exponential function looks like this, right? This is the exponential function. E to the power x. This is how it looks like, right? So basically, what it does is it scales up as the number gets bigger, right? It makes big number bigger. So as a result, it skews the distribution to having a long tail in the right hand side. So it looks like this. This is log normally distributed. I don't know what this is, so I probably shouldn't say for sure. Okay, so basically it looks like this. It's skewed, having a long tail. Now this property is not very important to us. I'm not sure that anyone spent time verifying whether this would have important implications. We use this. We have this because it allows us to solve the CARA investment problem with the following rule. And you have to remember this rule. The rule is, if x is log normal, right? If you have x is log normal, then the log of the expectation of x, right? The log of the average x is the expectation of log x plus half the variance of log x. So this is just something you memorize. This allows us to solve the CARA problem by taking log. The important part is it allows us to go from the expectation of the utility function to the utility of the expectation of the stock return. That's why we need this function. You see that we swap the position of the log x, the log expectation to become expectation log. This allows us to go from the this allows us to go from the log of expected utility to the expectation of the log utility. Okay, so you see when you see the math, you see why we have to do that. Okay, so let's do that. Right. So now CARA utility is ux equals to negative e to the power negative a x over a. Let's substitute in the final wealth for x. So it's WR plus theta s. So now you have a utility function. Okay. So we're gonna you get now the utility function ux equals to negative e negative a WR plus theta s a. All right. Okay, so we're now trying to maximize the expectation, right? We're trying to maximize the expectation. So to be more careful, I'll be more careful with the mathematical notation now. We're trying to find the optimal theta, right? We're trying to find the optimal theta. So the optimal, let's call that theta star. This is so this is the theta star is the theta that maximizes the expected utility of final wealth. Alright, so this is just mathematical notation, nothing special. So the optimal theta star, just maximizes the expected utility. The expectation is what causes so much trouble, because without getting rid of the expectation, we simply can't solve it. And we can't just directly take derivative when as long as the expectation is in place. So what we're going to do is going to make some transformation to make it into a form that allow us to use the rule that I just specified. Okay, so let's do that. The first step would be to just write down the utility function 2. So it's the expectation of what we have here, negative e to negative a to the power negative a times w plus r plus theta times s over a. The a doesn't really affect anything in this maximization problem, nor does the negative. However, so before I go on, let me just pull them outside. Now you can realize that you can directly pull all these terms out, right? That actually doesn't change anything right now. Okay. Actually, I don't have the part in the bottom anymore. Okay, so no negative either. Okay, so I haven't changed anything. It's just making use of the fact that negative 1 over a doesn't affect the expectation. You can just multiply it afterwards. However, if you want to take them out of the optimization, you have to realize that the negative sign would have flipped the function upside down, right? If you have a function, this is our original function, right? This is our original function. If you take out a negative sign, you would get this function. You'll be getting this function. Which means the maximization problem has just become a minimization problem. It has become a minimization problem. So now we're going to just remove negative 1 over a, but then we have to realize notationally we have now a minimization problem at hand. So it's argmin theta instead of argmax. Utility is preserved under monotonic transformation, strictly monotonic transformation, and log happens to be one of that. Log happens to be one of the strictly monotonic transformation. Now, as a convention in whatever courses I teach, log and ln means the same thing. I use them interchangeably. log and ln means the same thing. They both mean natural log. They both mean natural log. So, we can do this. I'm going to take a log of the expectation of e to the power awr plus theta s. Right? This is because utility preserved under strictly monotonic transformation. Right? Doesn't matter. Just scale. Basically, the idea is you're just scaling things up. Doesn't actually affect anything. But once we take log, and we have, if you take a look, what we have right now, we have theta at, now, the only thing that's random in this whole equation is S. The risky asset has a random return that's normally distributed. S is normally distributed, which means theta S is normally distributed. which means WR plus theta S is normally distributed, right? We're just adding and multiplying constant term. A is also a constant term, so now you still have a normally distributed. So everything is not. So now you have exponential. You have the exponential the exponent of negative A WR plus theta S. That's the whole thing. Is log normal distributed. So this is normal. Everything else is constant. So this is log normal. And that allows us to use the rule that I just specified. So you use the rule. You have arc mean theta. The expectation of log E negative A WR plus theta S plus the half of variance of log. It's very tiring to write all these things. E negative A WR plus theta S. And I have to make sure all the brackets are there. All right. The log is natural log, so it cancels out with the exponential function, and very nicely that leaves us with arc min theta the exponential function of negative A WR plus theta S plus half of variance of negative A WR plus theta S. And let's see. Negative A is a constant, WR is a constant, theta is a constant. Really, you can just take all of those things out from the expectation, right? It actually doesn't affect the expectation. The only thing that really leads the expectation is the S, which is random, right? For the variance part, you have a remember that when you pull out constant terms out of variance, right? You have to multiply, you have to square the term. So you have plus, you pull out the A, that becomes A squared. WR doesn't matter. WR, when you add a constant term inside a variance, they go away. So you can ignore the WR. You have to pull the theta term out, that becomes theta squared. And that you're left with the variance of S, right? So that's why I say you have to be very familiar with the statistics, the probability and probability, right? So you pull out all the terms, you leave with a surprisingly simple formula that you can take the derivative with. So let's take the derivative now. So the taking the derivative of the utility becomes taking the derivative of this function right here. So you take the derivative of this function, negative A WR plus theta E S plus half A squared theta squared variance of S. Okay, all right. This is actually not hard, and then you set it to 0, right? You set it to 0. This is actually not a hard math problem to do at all. It's actually very straightforward. You just take the derivative accordingly. You have negative A WR, that doesn't have any theta, that goes away. Negative A theta ES, that has a theta, so that becomes negative A ES, expectation of S, plus half A squared theta squared variance S, so the theta squared becomes 2 theta, right? So that cancels out with a half. So you are left with plus A squared theta variance S. I shouldn't need this at all because I have equate 0 in here. So rearrange. There's only a single theta here. Rearrange give you the solution to theta. That's equals to, if you rearrange, cancel things out, You have you have the expectation of S on top. The A cancel out with the A squared, because so that's just 1A here. It gives you a surprisingly simple solution. The dollar amount to invest equals to the expectation of the risky return over the rate of absolute risk aversion times the variance of the risky return. Okay. Simple. So it's surprisingly simple. So in our case, that would be mu A sigma square, right? Okay, so let's get some conclusion. Let's get some observation of this. So theta goes up if mu goes up, so higher average excess return, higher average excess return. A goes down, so that represents less risk averse. And if sigma goes down, that means less risk. So the formula makes a lot of sense. It's almost deceivingly simple. So the dollar amount invest goes up if there's higher average excess return. So it's always relative to the risk-free asset. That makes sense. Why invest in risky asset? Why invest in stock if you can get the same return from bonds? So the only reason why people are willing to invest in the stock market is because stock market gives you a higher return over bonds. You would want to invest less if you're more risk averse. You also want to invest less if there's more risk on the market. Okay, so the solution makes a lot of sense. But it's too simple in some sense. So you see in the next part right now. Okay, so it makes a lot of sense, but it's really simple. Okay, so